Lesson 54. Going to start talking about cables, and by cables I mean like someone comes and puts in a satellite dish or something for you, and they got a table that hitches up, not a table, a cable that hitches up the satellite dish to the house and so on. Turns out you don't want that cable to be too long because the signal gets weaker and weaker the longer the cable. But that's on page 2. On page 1, I want to introduce this phenomena. This phenomena is everywhere. It's a good phenomena to know about. Half-lives. Half-lives, I guess we're most familiar with half-lives when we're talking about radioactive stuff, right? So we'll just start with a radioactive example here. Element X is radioactive, and it has a half-life of 1,000 years. Now, what does that mean exactly? A half-life of 1,000 years means that in 1,000 years, half of it will be gone. And if you wait another 1,000 years, half of that will be gone. So you'll be down to 1/4, and so on. So every 1,000 years, you got half as much as you used to. So that's a characteristic of this element X. Every 1,000 years, it goes away. It doesn't like evaporate. What it does is it turns into a stable form or something. But I guess the radioactive particles are kind of going away. Anywho, we got 200 pounds of this stuff. Okay, that's right now. We got, call this now. So I'm going to have time going by on my sort of x-axis, except it's not an x-axis, it's a time axis, a t-axis. So that's time going by this way, and then this will be my pounds or whatever, my amount of stuff. And it says we're starting with 200 pounds, so maybe I'll go like, call this 20, 40, 60, 80, let's call this 100. 20, 40, 60, 80, we'll call this 200. And we start with 200, so right now, there we are. We got that much stuff sitting there. Now, if you wait 1,000 years, 1,000 years later, it's a half-life. So the 200 is now half gone, and you have 100. If you wait another 1,000 years, which means now we're out to the 2,000 year mark, half of the 100 is gone, which means now we're down to 50. And if you wait another 1,000 years and you get out to 3,000 years, the 50 will be cut in half, and you'll be at 25. So where's that? Somewhere around here. I think what I'll do is I'll write the number there to kind of remind me. That's supposed to be a 25. And so on. Now, what was the question? The question was, how much are we going to have left after 5,000 years? Well, we got to keep going then. If you get to 4,000 years, the 25 gets cut in half, and that'll be like a 12.5, I guess. Call it 12.5. And then you wait another 1,000 years, the 12.5 is cut in half, and it's going to be something like, well, cut that in half, you're going to get 6.25. So there's your answer. At the end of 5,000 years, the 200 pounds that you started with is now only 6.25 pounds. And notice, maybe I'll use it this way. Notice you get this interesting little, you could, I suppose, connect it with all straight lines, but I think you can tell it's kind of a nice little curvy, wurvy woo going down like this, gradually declining. You know what this looks like in electricity? That kind of looks like the discharge of a capacitor. There's another half-life phenomenon. You know, your capacitor is all charged up, and then you put the screwdriver on it, and it knocks you across the room. Or even if it doesn't knock you across the room, you put the screwdriver across it, the capacitor is going to discharge like this. This is also, if you were to put a very warm brewski in the fridge. The fridge is at this temperature, the brewski's at this temperature, it'll kind of go down like this. So you wait a little while, it's a lot colder. You wait a little while, it's a bit colder. So all kinds of things follow this kind of shape is what I'm trying to say. So, and it turns out signals and cables will follow this shape too. But let's stick to our radiation for a little while longer. Let's finish page 1 with radiation. What do you say? So I've kind of already got the basic idea across. That's what a half-life is. After so much time goes by, half. And if that same amount of time goes by, you have half again, and so on. What's example 2? Same element, element X. Okay, same half-life, 1,000 years. Okay. We want to have 10 kilograms left 4,000 years from now. Now you might be asking yourself, what kind of problem is that? Why would I want to make sure that in 4,000 years I've still got 10 kilograms of element X? And actually, here's an example. There's some guy out there, I was reading this article, he wants to make a clock that'll last, well, not forever, but he wants to make a clock that'll last like 1,000,000 years. And so it's going to have to be radioactively, nuclear powered. And so he's got to figure out, okay, how much fuel am I going to need if this fuel is still going to be working in 1,000,000 years, and so on. So, or if you send a satellite into space and it's nuclear powered, you want to have enough fuel that it'll still be working in 100 years or whatever. So this kind of problem comes up. The question for us really is, how would we visualize this? Okay, we get the same half-life idea. Every 1,000 years it gets cut in half. How much are we starting with? We don't know. That's the question. How much should we start with? We don't know what we're starting with. What we know is what we're ending with. We're ending with 10 kilograms after 4,000 years. Well, okay, then we know how to label our time axis. From now, we'll have to go out to 4,000 years. And in 4,000 years, we're going to have 10 kilograms. I think I'm going to label this the same as I did before. 20, 40, 60, 80, call that 100. 20, 40, 60, 80, call that 200. And let's hope this works. So I'm going to end with just 10 kilograms in 4,000 years. There's my 10 kilograms. So I must have had twice as much 1,000 years earlier. So my 10 must have been a 20, right? For the 20 got cut in half to 10 over 1,000 years. So going backwards, I'm doubling. So 1,000 years before that, the 20 must have been a 40. And 1,000 years before that, the 40 must have been an 80. And you see that it's starting to grow pretty quick here. 1,000 years before that, the 80 must have been a 160. So here's that nice curve again, that nice radioactive decay kind of a curve thing. And it looks like we kind of answered our question just by jumping like that. We're going to have to start with 160 kilograms if we want to end up with 10 in 4,000 years. So we moved this way for example 1, we moved this way for example 2, right? What else can I throw at you? It turns there's 4 types of problems I can throw at you, and that's why we got 4 problems on this page. What's another type of problem I can throw at you? Hey, same element. Element X is a star. Element X has a half-life of 1,000 years. Same situation. Every 1,000 years, it's cut in half. Barney's fossil has 1¼ grams. We assume that when Barney was alive, he had 80 grams. See, this is how they do that carbon-14 dating. They look at the fossil and they say, hey, this is how much carbon-14 you have. Well, you know what? Living things have this much, and you're dead. So if the half-life of it is 1,000 years or whatever, we can figure out, based on what you started with, what you ended with, we can figure out how old you are. Here's how that works. We know the half-life is 1,000 years. Okay, so we're going to be counting by thousands again. Half-life is 1,000 years. I don't know how far we're going to have to go, but there's 5,000 years to get started. Pretty good. This is now, that's, okay. His now has 1¼ grams. Okay, that's now, but we don't know where now is, so that doesn't do us a lot of good at the moment. We assume he had 80 when he was alive. This would be alive. And I guess this would be years gone by since he was alive, right? How many years have gone by since he was alive? So he started with 80. Maybe I'll count by tens this time. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And he started with 80. When he was alive, way back when, he had 80 grams of this stuff in him, whatever it is, element X. Okay, now we can start moving forward because of this idea that every 1,000 years it gets cut in half. The half-life is 1,000 years. So after 1,000 years, that 80 would have been down to 40. Right? And after another 1,000 years, the 40 would have been down to 20. Now we keep cutting in half like that until we get to this. Because it says right now we have 1¼ So we're going to have to keep going here, folks. So cut the 20 in half, and that's a 10, still too much. Cut the 10 in half, and it's a 5, still too much. Cut the 5 in half, and it's a 2.5, still too much. But if you cut the 2.5 in half, you'll end up with our magic number of 1.25 grams. So it looks like 6,000 years. So it should take 6,000 years for 80 kilograms to decay into 1.25 kilograms. Should take 6,000 years. Therefore, we can guess that this fossil is 6,000 years old. Plus or minus a little bit, but something like 6,000 years old. Pretty nifty-difty, huh? So it's all this half. There's that curve again. Put the warm one in the fridge and it cools like that. Okay. And then the fourth kind of problem. What are these first three kind of problems? You had the half-life. That's what I started with. What did I end with? Problem 2. That's what I ended with. What did I start with? Problem 3. I started and ended. How long did that take? What's the only other thing I could ask for? Well, what if we don't know? We don't know the half-life. Okay, so we know where we started. We start at 400, we end at 25, and it's going to take 18 years. So we know everything except the half-life. How can we do this one? Well, it's a little bit hard to label our times because we have no idea what the half-life is. Well, we start with 400. I guess we can kind of do it that way. Let's see, how should I do this? Maybe I'll call that 100. So every other one will be 100, 200, maybe that'll be 300. Call that 400. Okay, we started with 400. And we're going to decay to 25. Well, I don't know how long a half-life is, but I know that after a half-life, the 400 is going to be a 200. I know that. So this is one half-life. I have no idea how many years this is at the moment. I just know that that's one half-life. The 200 will turn into 100 after another half-life. The 100 will turn into a 50 after another half-life. And then we're going to get where we want to, which is the 25 after another half-life. So notice, we know this much. We had 1, 2, 3, 4 half-lives, right? Now this is something to keep in mind, by the way. Be careful you don't go like, let's see, we started with 400. Make sure you don't count like this. 1, 2, 3, 4, 5. That's not 5 half-lives. You don't count the numbers. You count the transitions or the jumps. 1 jump, 2 jumps, 3 jumps, 4 jumps. It's 4 half-lives, 4 jumps. I use the word jumps a lot when I'm playing with half-lives. So it's 4 jumps. Okay, now what else can we do with this? We started with 400, we ended with 25. We know it's going to take 4 jumps. And they're saying here that those 4 jumps took 18 years. Aha! See, now I know how to label this. That's 18 years. This is now times 0. That's 18 years. Halfway must have been 9 years. Right? And then halfway to 9 would be 4.5 years. And that's 1 half-life. So 4.5 years is 1 half-life for this element Z, whatever it is. Okay. So those are all 4 ways I can throw a half-life problem at you. Again, I can give you the beginning and ask for the end. I can give you the end and ask for the beginning. I can give you the beginning and the end and ask for how much time went by. I can give you the beginning, the end, and how much time went by and ask you for the half-life. What do you say we start putting in some satellite cables? Yeah, that's what we want, some satellite cables. Let's get this stuff back on the electrical road. Huh? Okay, cable A, which is a cable you might use. It'll say right on the box, cable A. And this cable A, and it'll say this on the box too, it'll say 5 half-lives every 100 feet. So if you reel out 100 feet of cable, in other words, if you install your satellite dish 100 feet away from the house, you'll need 100 feet of cable, and it's going to have 5 half-lives. The signal will be cut in half 5 times on its way from the satellite dish to the house. Ain't that something? Try not to make them 100 feet. Anyway, the input signal is 200. That's coming in. What will be the output at the end of an 80-foot length of this cable? Okay, I think what I want to do is I want to solve this problem two ways. The first way will be kind of making a graph like we were doing on the first page, just so it relates directly to the first page. The input signal is 200 milliwatts, so let's put a 200 right there. Now, we're going to jump half-lives. Now, we're not using time anymore. We're using length. How far down the cable are we going? There will be 5 half-lives every 100 feet. Well, do you see how that means there will be 1 half-life every 20 feet? Okay, it's a straight proportion if you want, or just 100 divided by 5 is 20. So if 5 half-lives needs 100 feet, then 1 half-life only needs 20 feet. So you can go like this, a half-life every 20 feet, 20, 40, 60, 80, 100. Cool. This is feet. This is the length of the wire, feet. The input signal is 200 milliwatts. We got the 200 right there. And so we know that when you get 20 feet down the cable, just 20 feet down the cable, your 200 is a 100. And when you go another 20 feet to the 40-foot mark, your 100 is going to be a 50 and so on. Now, how long do we want to use? We want to use an 80-foot cable, which means we're going to stop here. So, okay, take the 50, cut it in half again. 25, cut that in half again. There we are. We're going to end with a 12 and a half. So the power at the output end will be 12 and a half. What are these, milliwatts? Milliwatts. Okay, and we knew that because we knew we had to take 4 jumps. I solved that one faster than I thought I would. Okay, well, I want to give you a different way of doing this. Instead of always drawing graphs, be my guest if you want to keep drawing graphs. I love it when people draw things out because it means they're really piecing it through in their minds. It's awesome. But once you've done the graphs enough times, you might be able to just kind of say, here's the thing. It was 5 half-lives for every 100 feet. So the question was, how many half-lives would I have with an 80-foot piece of cable? And if you solve that proportion, you find out it's going to be 4 half-lives. So 4 half-lives means just take 4 jumps. Just take 4 jumps. You're starting at 200, right? Jump! It's 100. Jump! It's 50. Jump! It's 25. Notice that's only 3 jumps, right? The arrows are the jumps. 1, 2, 3 jumps. Jump one more time. There's your answer, 12 and a half. So once you know how many jumps you're supposed to take, you jump. You don't have to draw the graph. Saves you a little bit of paper, right? I'm going to do these last 2 the same way. Just take jumps. Back to example 6. Cable A has 5 lives per 100 feet. Is that the same cable? That's the same cable as 5. Cable A has 5 lives for every 100 feet. So I guess we already figured out. I'll write it down anyway, but we already did figure this out. Let's use purple. 5 half-lives every 100 feet. And, oh, wait a second. They don't give us the length of the cable. Well, now, we're going to have to start with with the powers. 64 goes in, 1 comes out. Notice the units are the same, milliwatts, milliwatts, so I don't have to get funky about changing units on the way. But 64 becomes 1. Okay. The 64 is going to become a 1 by taking a lot of jumps, a lot of half-life jumps. First, the 64 is going to be a 32 after so many feet. After that same number of feet, the 32 will be a 16. After that same number of feet, the 16 will be an 8. The 8 will become a 4. The 4 will become a 2. The 2 will become a 1. So notice that we went 1, 2, 3, 4, 5, 6. 6 jumps or 6 half-lives. To turn a 64 into a 1, or for the 64 to decay to just 1, it's going to be cut in half 6 times, 6 half-lives. So now we can start talking. We got 6 half-lives. Asking for the length of the cable. Well, now I can come back to what I was starting to do over here. I was saying, well, the cable has 5 half-lives per 100 feet. In this particular problem, we've got 6 half-lives. So how many feet is it? Set up a nice proportion. So half-lives in feet, you can just use nice proportions. So 5 half-lives, 100 feet, 6 half-lives, how many feet? Crisscross applesauce, 5x equals 6 times 100. And if you divide both sides by 5, you'll get that it can be 120 foot. 120 foot. Okay. Now, I don't know myself whether 1 milliwatt is enough of a signal to work your computer or TV or whatever. But if that's all you need is a milliwatt and you're starting with 64, you can have 120 foot of this cable. Okay, one more of these. Now this is cable B. This is a different cable. So we don't know if it's 5 half-lives per 100 feet or if it's something else. All right, what are we saying here? We got 20 milliwatts in, output 625 microwatts. So whenever they give you both the input and the output, the first thing I'm always asking myself is, well, how many jumps are we taking here? How many half-lives are we talking about? So maybe I'll just do that right away. If I take 20 milliwatts and I cut it in half once, it'll be 10 milliwatts. If I take 10 milliwatts and cut it in half, I'll be at 5 milliwatts. So notice that's 2 half-lives already. If I take 5 milliwatts and cut it in half, I'll be at 2.5 milliwatts. If I take that and cut it in half, I'll be at 1.25 milliwatts. If I take 1.25 and cut it in half, I'll be at 0.625 milliwatts, which, if you remember your table here that goes like tera, giga, mega, kilo, milli, micro, nano, pico, if you get the 0.625 here, milliwatts, and you want to slide your decimal to the right, that means your milli is going to become a micro. So this is actually 625 microwatts, which is great because that's what we're looking for, 625 microwatts. Therefore, we have just taken 1. Again, count the arrows, not the numbers. 1, 2, 3, 4, 5. We've taken 5 jumps. Now, what else do we know? How long was this cable? We want to know the half-lives per 100 feet. We want to know how many half-lives are there in every 100 feet. Half-lives in feet, you can always just get a proportion going. So how many half-lives in 100 feet? That would be the cable's rating. X would be the rating in half-lives per 100 feet. Okay, well, we had 5 half-lives in this cable. How long is this cable? This cable is 150 feet, actually. So you have to solve this one. So this is telling us that 150 times x on this diagonal is equal to 500 on this diagonal. And if you divide both sides by the 150, we're getting 3 1/3, I believe. 3 1/3 half-lives per 100 foot. That would be the rating of this cable. So I guess that cable A was it 5? 5 half-lives per 100 feet. This is a better cable. It's only 3 1/3 half-lives per 100 feet. That's the one I want. Okay. Don't lose as much signal there, you know. Okay, cool. So we've introduced this idea of using half-lives and figuring out cables. How does my input power decay to output power? Well, just keep cutting it in half, cutting it in half, cutting it in half. Every time you cut in half, I call it a jump. It's a half-life. And the cables are rated, depending on how the cables are constructed, they're rated in so many half-lives per 100 feet of cable. Okay, cool. So you should have enough here to start. No homework. Yeah, sure. Cool. Wow. Okay. I can dig it. I can dig it.